So now that we had a chance to talk about the various synchronization mechanisms that are available in Java built-in monitor objects, including the mutual exclusion capabilities provided by synchronized methods and synchronized statements, as well as the coordination facilities that are provided by the wait, notify, and notify all methods, let's go ahead and talk about some of the usage considerations to keep in mind when you apply or consider applying Java built-in monitor objects. The most important thing to note from this discussion is the fact that these built-in monitor objects have a bunch of traps and pitfalls that you have to be very wary of. So here are some of the traps and pitfalls that can befuddle you if you use monitor objects that come out of the box with Java objects. First and foremost, Java monitor objects are limited. Here are some of the reasons why they're limited. They don't support non-blocking operations because the locks always block, unlike, say, reentrant lock. They don't have sensible timed operations for the entrance queue portion, and they don't have the concept of interruptible behavior. So they're never interruptible, they are not timed, and they are always blocking. So those are things that you can get quite nicely with reentrant locks that don't work at all with the intrinsic lock that's part of the built-in monitor object portions of Java. Another problem, this is really the biggie, is there's only one wait queue. And there's also only one entrance queue, which may not seem like a big deal until you start trying to do more sophisticated data structures like, say, a linked blocking queue, where it really helps if you can differentiate a thread or threads that are trying to add something to the end of the queue or take something off the end of the queue versus add something to the front of the queue or take something off the front of the queue. So this is also a very major limitation. One of the consequences of this is you can end up with something called nested monitor lockout. And so you can read this tutorial for a discussion of nested monitor lockout. You can also take a look at the paper here below that's on my website that also discusses nested monitor lockout and shows some examples of what happens. What happens in nested monitor lockout is the following. We have a class here to illustrate this hazard, this quirk called buggy lock. And you can see how buggy lock creates a new object, which we call mmonobj. And then it has a lock method that will go ahead and be defined as synchronized. So that means that there's only one thread at a time that can be inside that critical section. And then what happens here is while locked is true, we're then going to go ahead and synchronize on mmonobj. But the problem is that lock still holds the intrinsic lock, and therefore unlock can never run because nobody can get inside of unlock because it's got the lock held. So anyway, very subtle problem, yet another reason to try to stay away from built-in monitor objects unless you're absolutely forced to do it, like, for example, someone gives you an assignment where you have to use them for something to teach you some behaviors of how they work. As I mentioned before, you can't do the two-lock queue optimization mechanisms that we were talking about that you would find in Java linked blocking queue. If we have time in the class, we might take a look at the linked blocking queue implementation. It's really cool, and it demonstrates a very nice use of two reentrant locks instead of one intrinsic lock to make things more efficient. Synchronized statements only support scope locking, so as a consequence, the lock that is released at the end of the curly brace inside the critical section, it'll always be released. And that is usually what you want, but there's actually certain cases where that's not what you want. And for those of you who are going to be implementing the graduate student version of assignment 3B, you'll see that there's actually a situation where it turns out that using a reentrant lock is better because you don't have to unlock the lock. And therefore, you can optimize certain things like checking or not checking conditions again, because you know that there was no opportunity for race conditions to sneak in during windows of time where a lock has been released. And we'll talk more about that when we talk about the next assignment. There's no sensible support in built-in monitor objects for timed waits. And that's just because the semantic of wait with timeouts is ridiculous. And you can take a look at this link below for some discussions about that. Another very vexing issue with built-in monitor objects is trying to choose between notify and notify all. And so We had talked about this before in the context of condition objects. Now we're going to revisit it in the context of built-in monitor objects. So if you recall from our previous discussion, you can use notify instead of notify all when two conditions hold. One is that you have something called uniform waiters, which means that all threads that are waiting for the same condition, like not empty or not full. And then the other one is the one in, one out condition, which says that a notify on the monitor object is designed to enable at most one thread to go forward. And it turns out that that actually doesn't apply when you're doing built-in monitor objects for things like our queue. And the reason for that is that our queue has threads that are both waiting for the condition to be not empty and the condition to be not full. And since there's only one monitor condition, then you don't have uniform waiters. You have non-uniform waiters because they're not all waiting for the same condition. So as a result, you can't use notify. Using notify is always desirable whenever possible because that avoids the thundering herd problem that we've talked about, whereas using built-in monitor objects tends to incur the thundering herd problem in many use cases, unless you go to the trouble we're going to go to in assignment 3B, where you're going to have essentially a queue of monitor objects, and then you just notify one at a time. And this, again, is the limitation for something like our simple blocking bounded queue, where we only have a single monitor condition, and therefore we have to use notify all over the place. There are also some other subtleties here that may not really appear obvious at first glance, and it has to do with fairness issues that arise in terms of the order in which waiting threads are notified. And the default behavior of Java built-in monitor objects is to use a semantic known as haphazard notification. And that just means that the underlying hardware, the underlying Java execution environment decides the next thread to implement, to let run, to schedule and start running. It's not really all that haphazard, but it appears that way to users because they have no control over it. If you want to get control, then what you need to do if you're using built-in monitor objects, and for that matter, if you're using condition objects too, is you need to use something called the specific notification pattern. And we're going to talk about specific notification here shortly, and that's going to be important for your next assignment. So you can take a look at the link at the bottom of the page for more information about specific notification. What that pattern does, as we'll see, is it allows the implementer of the pattern to programmatically choose a particular thread to run next from a family or a set of waiting threads. In practice, you typically need more than Java's built-in monitor object mechanisms. You typically need to use Java util concurrent features or Java util concurrent locks features like reentrant lock and condition object. So take a look, as we've talked about before, to our previous discussions of reentrant lock and condition object for more about those particular mechanisms. As you can see here, for example, in the array blocking queue implementation, which is a much more production-ready industrial strength implementation of our simple blocking bounded queue, this does the same thing. It just uses reentrant lock and a couple of conditions, so it's a lot more optimized. There's also other parts of Android, for example, that use monitor-like mechanisms. Android's concurrency frameworks implement a very cool message passing mechanism using, again, under the hood, reentrant locks and condition objects and so on, and other synchronizers. And they allow you to be able to do some very cool coordination issues with multiple threads that don't require the use of Java built-in monitor objects. In fact, the message passing mechanisms that are so prevalent in Android and other concurrency frameworks may allow you to completely avoid the use of the monitor object pattern and synchronization altogether, which can be very powerful and liberating because a lot of these race condition issues just completely disappear once and for all. So that's the end of our discussion about Java monitor objects and the usage considerations. So at this point, you should have a lot of knowledge about how to compare and contrast the condition objects with the Java built-in monitor objects, know when to use one, know when to use the other, and with assignment 3B, you'll get a chance to put a lot of this into practice.